All right. So this was midterm 2. One thing that I want to point out that I'm sure some of the people here know because I've done it to them before, but I have a tendency to be kind of mean and put extra credit opportunities in the instructions, which is sort of my like way of reminding people that you should read the instructions for the exam. These typically take the form of me either asking you to tell me a joke or asking you to solve some very simple arithmetic thing that you'll usually get wrong. It's fine. It's great. But it's free extra credit for just reading the instructions. It's not on every test, but you should still read it just in case it's there. So it might happen again this semester. Um, Regardless, after that, let's go ahead and move into the first problem. And problem number 1 was the derivative of tangent. I wanted a proof here, right? So the easiest way to do this is using the quotient rule. So the derivative of tangent is the derivative of sine over cosine, which is, so we'll use the quotient rule for this. It'll be the bottom times the derivative of the top, which will be cosine x times cosine x, minus the top times the derivative of the bottom, which will be sine x times negative sine x. And all of that gets divided by the bottom squared, cosine squared x. The negative signs can cancel, and we can combine some stuff here. We get cosine squared x plus sine squared x over cosine squared x. And then from there, cosine squared plus sine squared is 1 by the Pythagorean identity, which leaves us with cosine squared x. 1 over cosine squared x, which is, of course, secant squared x. I think we did this proof. Did we do this proof in class? I feel like we did this proof in class. Either that or I assigned it to you at some point. It was definitely on the review sheet, so it was hopefully relatively straightforward. I guess something I should mention going forward is that while I will probably not require you guys to memorize every single identity in the world, knowing your Pythagorean identity is really important, right? Knowing that cosine squared plus sine squared is 1 is something that you guys should definitely know. So I'm definitely not going to assume at every turn that you guys have memorized every single sum identity or difference identity, but certainly Pythagorean identities are on the table. Any questions about this first problem?
Nope.
Uh, Transition from the written equation to the first step. How'd that come to be?
Taking the, what do you mean? Taking the derivative of sine over cosine? It's a
Yeah.
quotient rule. That's the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom.
Or do you mean that the tangent equals sine over cosine?
Which I guess technically that's a what's called a quotient identity, but honestly, to me that's the definition of what tangent is to some extent. Like it's the first thing I think about when I look at tangent. And I encourage you guys to look at it the same way. Does that answer your question, Tyler?
Yeah.
Okay.
I got it mixed up and I thought it was you have to do the same thing as the product rule, put cosine on the other side of sine squared. And, oh, that hurt.
Yeah. All right. So the next problem was a couple of quick derivative problems. These ones, if I remember correctly, they're not too awful. For number 1, we want to rewrite it just a little bit. That'll be 3x to the fourth plus, I want to write this as 6x to the negative 1/2 instead of 6 over the square root of x. And then we can take the derivative. So f prime of x, the first part is very straightforward. It just ends up being 12x cubed. The next part is a little bit trickier, but it's not that much trickier. That'll be, minus 3x to the negative 3/2. If we want to write this in a slightly more simplified version, that'll be 12x cubed minus 3 over the square root of x cubed. The negative part sends it down to the denominator. The 3 stays as a power, and the over 2 turns into a square root. Any questions on that one? All right. Moving on to part B of this problem. This is a chain rule, but it's a relatively simple one. So your inner is 5x plus 12. Your outer is x to the 2020. The derivative of your inner is just 5. And the derivative of your outer is 2020 x to the 2019. So when we put this all back together using the chain rule, we get 2020 times 5, oh, good grief, 5x plus 12 to the power of 2019 times 5. And from here, we can simplify these two coefficients. We can multiply 5 times 2020 to give us that g prime of x is, in fact, 11,000 times 5x plus 12 to the power of 2019. And that's your derivatives. Any questions about this second one here? So for what it's worth, I will also post a copy of this to D2L. So when I'm done with this, I will export it to a PDF file and post it so you guys can look at it later. Awesome. Let's move on to problem number 3 then. So problem number 3 was a graph, right? And I asked you to look at this graph and tell me the points at which it's not differentiable, right? So a reminder that f of x is not differentiable means that the derivative doesn't exist. And the derivative is sort of like, it's a limit, right? It's a limit of the slope from the left and the slope from the right. So here and here, your slopes are different, right? So the limit can't exist, so derivative can't exist because it can't agree. And then there's 2 more spots where the derivative doesn't exist, here and here. At these 2 spots, the function is not continuous. Because the definition of the derivative involves the value of the point at that point, right? The definition of the derivative is the limit as h approaches 0 of f of a plus h minus f of a over h. This f of a part implies that the function must exist. Oh, sorry about that freak. Whoa, good lord. Sorry about that freak out there. So we have 4 different places where the derivative doesn't exist. The derivative doesn't exist at x equals -4, at x equals -3, at x equals -1, and at x equals 2. For each of these singular points, explain why f of x is not differentiable there. So at -4 and -1, the left-hand slope and right-hand slope don't agree. And for x equals -3 and x equals 2, f of x is not continuous. Or more specifically, actually, f of x does not exist. Or f of -3, I should say. And f of 2 does not exist. Any questions about this problem here? We did a very similar problem to this in class, I believe. All right, I don't hear any shouting or see any shouting on chat, so we'll keep going. Problem number 4 is another differentiation problem. This one is implicit differentiation, so it's a little bit different, but it still is not too awful. So we're taking d over dx of 3xy squared minus 5 is equal to 2 times the sine of y. For the left-hand side, we need to use a product rule for part of it. Because we have 3x times y. So that'll be 3x. So the first times the derivative of the second times 2y y prime. Whenever you differentiate a y, you should involve yourself a y prime here. Plus 3 times y squared. The second times the derivative of the first. The derivative of -5 is 0. All constants disappear, right? And then on the right-hand side, we take the derivative of 2 times sine of y to give us 2 cosine of y times y prime. From here, what needs to happen is we need to simplify some stuff so it just looks a little bit nicer. Then we're going to collect our y prime terms on one side and everything else on the other side. Then factor out y prime. So over here, 3x times 2y y prime can turn into 6xy y prime plus 3y squared. And 2 cosine of y y prime is, I don't know, 2y prime cosine of y. I'm going to subtract the 6xy y prime over to the other side to give us 3y squared is equal to 2y prime cosine of y minus 6xy y prime. And then we can factor out our y primes, giving us that 3y squared is equal to 2 cosine of y minus 6xy times y prime. And from there, we just need to divide by all the stuff that's not y prime over here. So we'll divide by all of that. That gives us that y prime, or dy dx, is equal to 3y squared divided by 2 cosine of y minus 6xy. So that's the problem for number 4 here. It's just a quick implicit differentiation. Maybe the trickiest part is actually simplifying it, actually. Solving for the y prime. Yes.
So, uh, can the very first step,
Yes.
the 3x times 2y y prime, can can you talk me through how you get to that step?
So we're trying to take the derivative of 3xy squared, right? And in order to do that, we have to apply a product rule. So in our product rule, our first function would be 3x, and our second function would be y squared, right?
Oh, okay.
Yeah.
Okay, that makes a lot more
The
sense.
derivative of the first would then be 3, and then the derivative of the second would then be 2y prime.
Okay.
Yeah.
Okay.
So
Thank you.
that's our product rule. Cool. Any other questions about this one? Right. So problem number 5 was here's one function, take the derivative of it in 3 different ways. The first way I asked you to use the chain rule is extremely similar to, I think, number 2b, but with smaller numbers. So here, oh, wow, that was horrifying. Here we would say that f prime of x would be 2 times 2x plus 1 times 2. That's the derivative of the outside. The 2 comes down in front, right? And then we multiply by the derivative of the inside, giving us 4 times 2x plus 1, which is 8x plus 4. So we should get 8x plus 4 as our final answer for every single one of these. Otherwise, we've done something horribly wrong. So here, we're going to use the product rule for part B. So it'll be the first times the derivative of the second. So f prime of x would be 2x plus 1 times 2, plus the second times the derivative of the first, which would be 2x plus 1 times 2 again. When we distribute these, we get 4x plus 2 plus 4x plus 2, which gives us exactly, again, 8x plus 4. So obviously for these problems, the answer is not that relevant, because once you get one of the answers, you have the answer for all of the rest of them. What I care about is you doing the different rules I asked you to, so you should show some amount of work on the way there. I'm not saying that you have to do the first, second derivative of the first derivative of the second, but you definitely needed to at least have something there that told me you use the product rule. Finally, for part C, f of x is small enough that we can multiply it out and then just use the derivative that way. So f of x is 2x plus 1 squared, which means that it's also the first would be 4x squared plus 4x plus 1. And from here, we can just use the power rule. F prime of x is 8x plus 4. So, same answer, 3 different ways. Any question about any of these 3 problems? Okay, let's go ahead and move on to number 6. Number 6 is our first short answer problem. For each of the following statements, give a well thought out answer in complete sentences. You must justify your answer to receive full credit. Okay. So question A here, let f of x be differentiable everywhere. Suppose that f of 3 is equal to f of 5, which is equal to 2. Does f of x have a horizontal tangent line at some x coordinate on the interval 3 to 5? So this is the requirements for MVT, the mean value theorem, right? So the mean value theorem, MVT, guarantees that somewhere on 3 to 5 there exists C such that f of C is equal to, or sorry, f prime of C is equal to f of 3 minus f of 5 over 3 minus 5. But f of 3 minus f of 5 is 2 minus 2 over 3 minus 5, which is 0. So there exists C in 3 to 5 such that f prime of C is equal to 0. Essentially, if your explanation or your sentences involved you invoking the mean value theorem and stating that the mean value theorem guarantees that there is a horizontal tangent line in there, I should say that I suppose I didn't quite finish. If f prime of C equals 0, then f of x has a horizontal tangent line at x equals C. But again, if your explanation involved MVT that guarantees that there should be a derivative equals 0 somewhere on that interval, then that's pretty much good enough, as long as you invoke the MVT. That's what I was looking for. Pictures are also good for this sort of thing, right? Like if you had drawn a little picture that had 3 and 5 here, and then 2 here, and then drawn a function in there, somewhere there has to be a horizontal tangent line in there as well, as since it was horizontal at the top there. Any questions about this MVT problem? All right. So for part B, we're talking about the same function. Does f of x have a local minimum or local maximum on 3, 5? If yes, explain why. If no, give a counterexample. So this one's sort of a trick question. Note f prime of C equals 0 does not mean that there must be an extrema at x equals C. For example, let f of x equal 2. If f of x is the constant function 2, then it has no local minimums or local maximums. So it clearly does not have a local minimum between 3 and 5. However, it does technically have a horizontal tangent line at every single point. We could pick any value between 3 and 5 we wanted, and we'd get that horizontal tangent line. So We have no max or min between those. Any questions? All right. What is the thing that you struggled most in this unit? So, spoilers, I don't actually grade these for correctness because there is no correctness for this. If you answered the other parts and didn't answer this for some reason, I would probably take off a point or two. But if you answered this and you answered this question, then I gave you the points. So this is just for me to sort of gather data and see, like, hey, what was the thing that the class struggled with the most? What was each student struggling with, etc.? Are there things that I need to go back and go over? All right. So for problem number 7, it's very similar to problem number 1. I think this was by far the most crossed off problem on the test, and reasonably so. You can either do this using the inverse function theorem, or you can do it using implicit differentiation. The inverse function theorem version we did in class, so I will do the implicit differentiation version here. So let y equal ln of x. Then e to the y equals x. That's just a property of logarithms. That's the definition of the logarithm. It is the inverse to the exponential function with its base. In the case of the natural log, the base is e, right? So let's differentiate implicitly. We'll take d over dx of e to the y is equal to d over dx of x. The derivative of e to the y is, of course, just e to the y times y prime, right? And the derivative of x is just 1. We can divide both sides by e to the y, which tells us that y prime is equal to 1 over e to the y. But e to the y was equal to x from above, right? So y prime is equal to 1 over x. So the derivative of ln of x is equal to 1 over x. So that's the proof for ln of x. It's a little bit more straightforward and easier than the arctangent, arcsine, arccosine ones. It doesn't involve any weird triangle voodoo. It's just pretty straightforward through implicit differentiation. Or you can use the inverse function theorem. The inverse function theorem says that f inverse prime of x is equal to 1 over f prime of f inverse of x. So that means that the derivative of ln of x is equal to 1 over e to the ln of x, which is just 1 over x. So totally viable. In some sense, the inverse function theorem is actually a special case of implicit differentiation anyways, so it's not the most essential thing that we could think of. Any questions about this proof before we move on? All right. So number 8 is another couple of take the derivative of these two functions problem. These were this first one is a chain rule, so the inner is 2x cubed plus 3x squared. The outer is arctan of x. The derivative of the inner is 6x squared plus 6x, and the derivative of the outer is 1 over x squared plus 1, or 1 plus x squared. It doesn't matter, actually. So our derivative total, f prime of x, should be 1 over 2x cubed plus 3x squared plus 1 times 6x squared plus 6x. And if you want, you can simplify this a little bit. We can FOIL out the stuff in the denominator there. So we get 6x squared plus 6x over, what do we end up with here? We end up with 4x to the 6th plus 12x to the 5th plus 9x to the 4th plus 1. You probably got most of the points if you got to, whoops, that's too early. If you got to here, that's worth most of the points. If you simplify it a little bit further, that's worth all of the points. For what it's worth, this simplification is not that particularly helpful, so I don't know how many points I would be taking off for leaving it in the first form. Any questions about 8A here? All right, let's take a look at 8B real quick. This one's just a quotient rule. Our upper function is 3x squared plus 4. Our lower function is 3x minus 5. Our derivative of our upper function is 6x. The derivative of our lower function is 3. So now we just need to put it together. Low d high minus high d low, all over low squared. So low d high is 6x times 3x minus 5 minus high d low would be 3 times 3x squared plus 4. All divided by 3x minus 5 quantity squared. This one we can simplify. 6x times 3x is 18x squared minus 30x minus 9x squared minus 12, all divided by 3x minus 5, which is 9x squared minus 30x minus 12 divided by 3x minus 5 quantity squared. You could check this to see if anything cancels here, but I don't. 3x minus 5 can't be a factor of 9x squared minus 30x minus 12. 5 doesn't divide 12, so we shouldn't get any cancellation here. I guess the last thing you could do if you really wanted to is to FOIL out the denominator, giving us 9x squared minus 30x minus 12 over 9x squared minus 30x minus 25. Sorry, plus 25. Which looks surprisingly similar and weird, but they shouldn't share any common factors, so nothing should cancel. Any questions on this quotient rule? For what it's worth, if you just left it like this version here, without foiling out the denominator, I probably would give full credit for that. That's perfectly fine. You just do want to actually collect the terms in the numerator, I think. All right, let's move on to problem number 9 then. Number 9 is another short answer problem. For each of the following statements, give a well thought out answer in complete sentences. You must justify your answer to receive full credit. When using implicit differentiation, why do we have to multiply by a y prime every time we differentiate a y? So here, implicit differentiation lets us take the derivative of y by implying that y is a function of x. Therefore, the chain rule mandates multiplying by the derivative of y. We don't know what that is. That's what we're trying to find, so we call it y prime. So every time we're differentiating a y, we're using the chain rule because y is implied to be a function of x. So we're using the chain rule to then multiply by the derivative of y. If your explanation involved any sort of y is a function of x or the chain rule, you probably got full credit for this problem. Assuming that you're using full complete sentences and what you wrote made sense. So part B here for this short answer is asking what is a critical point, how do you find them, and why are they useful? So a critical point is anywhere f prime of x is equal to 0 or f prime of x does not exist. They're important because they are the only place f prime of x can change signs. So they the set of all critical points contains all maximums and minimums. So if you answered this question by giving me the correct definition of what a critical point actually is, that a critical point is anywhere that the derivative is equal to 0 or doesn't exist, then that was the first part, right? And then the second part is saying that they help you find mins or maxes, or they're the only place the derivative can change sign, that sort of thing. One of those would have gotten you credit. Okay. You needed both the definition and some statement about why they're important that was vaguely correct, that made sense in order to get full credit on this problem. Any questions about these short answers? All right. And once again, part C is just a it's just a question for diagnostics. So as long as you answered it, you got points for it. Coming in on the home stretch here, this is problem number 10. So we're talking about the unit circle here, x squared plus y squared is equal to 1, which is the unit circle since it's the circle centered at the origin with radius 1. And first we're going to find dy dx by solving for y, then taking the derivative conventionally. So here we're going to say that y is equal to, y squared is equal to 1 minus x squared, which means that y is equal to plus or minus the square root of 1 minus x squared. For simplicity here, assume positive root. So then dy dx is equal to 2x over 2 times the square root of 1 minus x squared, which is x over 1 minus x squared, square root of. This is a chain rule. It's a little bit tricky to sort of just do that quickly, but the gist of it is that the inner function is 1 minus x squared, and the outer function is the square root of x. The derivative of the inner function is, sorry, that should be a negative in front of it. Negative. That should be a negative 2x. And the derivative of the outer function is 1 over 2 times the square root of x. If you rewrite the square root of x as x to the 1/2 and then you go through it that way, you'll get a slightly different answer. I think you end up with negative x times 1 minus x squared to the negative 1/2. So you might end up with something like negative x times 1 minus x squared to the negative 1/2. That is also okay. If you do it implicitly instead, we start with y squared plus x squared is equal to 1. We take the derivative of both sides. We get dy over, 2y times dy dx plus 2x is equal to 1, equal to 0, which means that 2y dy dx is equal to negative 2x. And we can divide both sides by 2y, which gives us that dy dx is equal to negative x over y. Notice that this agrees with the previous problem, right? Negative x over y is the same as negative x over the square root of 1 minus x squared, assuming that since y is the square root of 1 minus x squared there. Any questions about either derivative? I kind of went through them sort of quickly. All right. And then the final part of this question is using either of the two derivatives, find the equation of a line tangent to the unit circle at this point here. I want to use the implicit derivative because it seems nicer, and I gave you both the x coordinate and the y coordinate here. So we can say that, so that means that dy over dx is equal to, that will be negative square root of 3 over 2 divided by 1 over 2, which would in fact be the square root of 3 over 2 and the 1 over 2, the denominators can cancel, leaving us with the square root of 3. So that means that the equation of our tangent line is y minus 1/2 is equal to the square root of 3 times x minus the square root of 3 over 2. We can simplify this if we want to. This gives us that y minus 1/2 is equal to the square root of 3 times x minus, I just said the square root of x times x, that's not true. Square root of 3 times x minus 3 over 2. And then we add 1/2 to both sides, so we get y is equal to the square root of 3, good lord, square root of 3x minus 1. And that is your tangent line. For what it's worth, this version of it, if you just left it like this, I think I told you that you can leave the equation of the tangent line as is for the most part. So if you left it like this, I think I was okay with that. Any questions about this tangent line here? All right. I think a couple more derivative problems here. Find the derivative of the following functions. So this one's a little tricky. This is a double chain rule. So it's a chain rule. The inner function, to me, I would say that the inner function here is actually sine of x cubed. And the outer function is x squared. The derivative of the inner function here, we need to use another chain rule with an inner function of x cubed and an outer function of sine of x. So the derivative of the inner function is 3x squared, and the derivative of the outer function is cosine of x. So the derivative of sine of x cubed is 3x squared times cosine of x cubed. The derivative of our outer function is just 2x. So our final answer is that f prime of x is, so it's the derivative of the outer with the old inner, so that would be 2 times sine of x cubed times the derivative of the inside times 3x squared cosine of x cubed, which is 6x squared sine x cubed cosine x cubed. If you really, really wanted to be fancy here, 2 sine x cosine x is a double angle identity, so you could do that if you wanted to, but you absolutely do not. That is not required by any extent. This version is fine. So this one was it was a nested chain rule, but if you break it down into its component parts, it's not too bad, I hope. For what it's worth, you also could have done it as the inner function is x cubed and the outer function is sine squared of x. Then you would have had to do the chain rule for your outer part instead. You end up in the same spot at the end. Any questions about this guy before I go on? All right. This one here is a pretty straightforward product rule. Our first is x squared. Our second is ln x. The derivative of the first is 2x. The derivative of the second is 1 over x, which, if you were clever, you noticed that this was actually given to you, I think, in problem number 7. So you didn't even have to memorize the derivative of ln of x. Just the proof for it. And then we're just using the product rule as we would normally. So that would be the first times the derivative of the second. So that would be x. G prime of x is x squared times 1 over x plus the second times the derivative of the first, which would be 2x times ln x. We can simplify this first part pretty easily. X squared over x is just x. So x plus 2x ln x is our answer. All right. Any questions before we move on to the very last problem here? All right, let's look at number 12. So number 12 was a bit of a bear. It was a quotient rule with 2 chain rules inside of it. So I left it on a problem of its own, but it's still just a derivative, and if you break it apart into its bits, it shouldn't be too awful. Okay, so for the quotient rule, we want to do the top, which is the square root of 5x squared minus 4x plus 12. And the bottom will be e to the 12x. The derivative of the top we would have to do a chain rule where our inner function is 5x squared minus 4x plus 12, and our outer function is the square root of x. The derivative of our inner function is 10x minus 4. The derivative of our outer function is 1 over 2 square root of x. So the derivative of our top should be, well, okay, so it'll be 10x minus 4 divided by 2 square root of 5x squared minus 4x plus 12. We can cancel down a little bit and leave us with 5x minus 2 divided by the square root of 5x squared minus 4x plus 12. The derivative of our bottom function is also a chain rule. But this one is probably a little bit easier than the previous one. Our inner function is 12x. Our outer function is e to the x. The derivative of our inner function is 12. The derivative of our outer function is still e to the x. So we just end up with 12e to the 12x. And now we just need to put our pieces together in our giant awful quotient rule, right? So that means that f prime of x will be, so low d high will be e to the 12x times 5x minus 2 divided by the square root of 5x squared minus 4x plus 12 minus the top times the derivative of the bottom, which would be the square root of 5x squared minus 4x plus 12 times 12e to the 12x, all divided by e to the 12x squared. One nice simplification step that you can definitely take at this point is that we actually have an e to the 12x in every single term here. We have one here, we have one here, and we have one here. So we can cancel those all, which leaves us with f prime of x is 5x minus 2 over the square root of 5x squared minus 4x plus 12 minus 12 times the square root of 5x squared minus 4x plus 12, all divided by e to the 12x. There's theoretically some small further steps you can take here to combine some things. You could multiply this term by the square root of 5x squared minus 4x plus 12 to get a common denominator and combine those guys, but honestly, this is fine. This much simplification is okay. It doesn't get much nicer than this gets, so this is good enough. And if you didn't spot the fact that you could cancel the e to the 12x's, I probably wouldn't be that upset at that either. And that was the second midterm. It was pretty heavy focus on just taking the derivatives. There was a little bit of implicit differentiation and other stuff. But for the most part, I was just aiming at making sure that you felt comfortable doing derivatives and comfortable with a handful of concepts about differentiation and stuff like that. Do you guys have any questions about this exam?
Are grades gonna be posted like right after this or
what? Grades? Or are you asking about grades, Ilsa?
Yeah, grades or like the graded
Yes.
exam.
That would be something that would be good for me to have done.